So in this example problem, we're asked to determine the deflection and the slope at point A. So we're looking for delta A and the slope theta A at point A. And we're told to ignore the strain energy due to transverse shear. Okay? So in this problem, we have a cantilever beam that's fixed at point B here, and we have an applied load at point A. Okay? So the first thing, so for Castigliano's method, we know that delta A would be equal to du dp at point A. Alright, so in the simplified method, we know that it's going to be equal to the integral from 0 to L over 1 over e to the iz times the moment z with, and then times the derivative of the moment z with respect to our applied force PA dx. Okay, so we need to first determine, in order to apply it, we need to determine our moment z as a function of x. Okay, so to determine that moment, we can take a section cut at any point x, and we can apply our internal forces, our moment at a moment about the z-axis of x, and our internal our shear force v of x. All right. So if we sum all of our moments about the z-axis and set them equal to 0 for our section cut here, so like the left-hand side here, what we end up getting is we get p times x plus m of x. Alright, there's no other forces or anything else being applied to the system, so that's our total of all of our forces. So our m of x term is just going to be equal to minus p of x. Minus p times x. Alright, so that's our variable. Okay, so we can plug our minus p of x term into here, and then we can take the derivative of that moment with respect to PA. So if we do that, get the derivative of mz of x with respect to P. Alright, applied at our point of interest. So in this case, our point of interest is at A. So we would end up getting negative x. So we can plug in our negative x into this term here. Alright, so what we end up getting is, for this integral, is we end up getting e and iz in this case are constants, so we can take them out. So we have our integral would be equal to px squared dx. Alright, so then what we should end up getting here is we get 1 over e to the iz p times x cubed over 3. Alright, from L to 0. So if we plug in length in 0, we get p over 3e to the iz times the length cubed minus 0 cubed. So our displacement at point A is going to be equal to p L cubed over 3e to the iz. Alright, which was the same value that we got in last lecture. Alright, so we can do a similar process for delta A. Okay, sorry, theta A. So we want to find the slope at point A. We just have to take the derivative of our strain energy with respect to the moment applied at point A. Alright, so we know that using the simplified Castigliano's method, that would be equal to 1 over e to the iz times minus times the mz of x times the derivative of the moment with respect to the mz of x with respect to the concentrated moment at point A dx. Alright, so we need to calculate what mz of x are and what mz of x is and what the derivative of mz of x with respect to the concentrated moment is. So if we create another section cut, alright, at an arbitrary location x, and at point A we have our concentrated force P, alright, and then we apply a dummy moment, okay, which we're going to call M of A here, alright. We can then on the opposite side of our beam where we took the section cut, we have to apply our internal forces. So we're going to have our shear force V and our applied moment M. Alright, so this would be our mz of x term. So if we sum all of our moments about the z-axis, and we set them equal to 0, and we do it about our section cut, so at x equal to 0, what we end up getting is we'll get p of x plus ma plus mz of x. Right? So what we end up getting for mz of x is we get mz of x is going to be equal to minus p of x minus ma. Okay, and then the derivative of mz of x is going to be with respect to ma is going to be equal to just -1. Alright, so we can plug these two values here into our equation above, and if we do that, I'll draw it down here, is what we're going to get is our theta A term is going to be equal to the integral from 0 to L 1 over e to the iz times negative p of x minus ma times -1 dx. Alright, so if we multiply all this through, what we end up getting is we get our integral from 0 to L 1 over e to the iz p of x plus ma dx. Okay, so after we have done this, we can now after we've taken our differential, we can now set m of a equal to 0 since it's our dummy load. So then our integral gets simplified down a little bit more. It just becomes 1 over e to the iz times p x dx. And we do that integral, what we'll end up getting is we'll get p over e to the iz x squared over 2 from L to 0. And then what we end up getting is if we evaluate the bounds from if we evaluate that using the bounds of our integral, we'll end up getting just p L squared over 2 e to the iz for our slope, which matches what we got in the same example problem in the last lecture using the original Castigliano's method. Okay, so in short, using the simplified Castigliano's method, it'll simplify your integrations a little bit, and it makes your calculations a little bit simpler, especially as we get into more complex loadings. So please use the simplified Castigliano's method whenever possible.